Okay, everybody, sorry for the late start. um, so last semester, I, Star Wars references are sort of my favorite. So I said something in passing about the Book of Boba Fett, and somebody in the back said, "Hey, wait, man, spoiler alert!" I said, "That episode's been out 2 weeks. I mean, if you haven't watched it yet, that's on you." And he appropriately responded, "Dude, you've been giving me all the homework, so I have no time to watch the Book of Boba Fett." And I said, "Okay, fair point, fair point." So, looks like we're somewhat few in number. Many of your classmates are taking the exam and catching up later, so it's understandable. I'll try to give you all the secrets today to reward you for being here. Let's see. So, we have been talking about reaction mechanisms, and we dealt with a substitution reaction where I showed you maybe three possible mechanisms, one of which we ruled out because it broke the octet rule. And then there were a couple more which we thought were legitimate. And the first is that we make the new carbon-carbon bond at the same time. Oh, lovely. Apple Pencil battery slow. We make the new carbon-carbon bond at the same time as we break the carbon iodide bond. And that would presumably go through this transition state where the bond between carbon and iodide is breaking at the same time as Cn minus is coming in. No longer full negative charges on Cn minus and I minus. And then here's the substitution product. Just to introduce a little bit of terminology that we're going to have, we're going to call Cn minus the nucleophile. Well, I guess that's no surprise. And we're going to call I minus the leaving group because it leaves. Surprising. Okay. And we mentioned that if this all occurred in one step, we could expect a free energy reaction energy landscape looking somewhat like this. Presumably along the x-axis we have, I don't know, some measure of reaction progress. You could either do the carbon-carbon distance or the carbon iodide distance, one of which would be decreasing and the other would be increasing as an indicator of reaction progress. We talked about activation energy, which is what controls the rate of the reaction. We said that when you form and break bonds at the same time, that's a concerted reaction. And I will point out one thing that's really important for arrows and mechanisms, especially at this stage. Later on, we'll relax this a little bit, but right now I want you to be good at this, and that is if you show multiple arrows in the same set of, I don't know, structures, you are communicating that both of those things happen via a single transition state in a single step. All right, so this is not just an indication of what happens, but how it happens. And the way we will push arrows for this type of reaction mechanism is different from how we will push arrows in the next reaction mechanism. We said that this is called an SN2 reaction, S for substitution, N for nucleophile, and 2 for bimolecular. That reflects the fact that there are two concentration terms in the rate law, and those reflect the fact that this single transition state involves Cn minus and your alkyl halide starting material. And experimentally, we could test whether this was the case simply by measuring the rate of the reaction. There are a lot of techniques for doing this, and we won't go into those now, but if you want to know more, you can talk to people in the Michaelis lab or the S lab who have some experience working with folks that do this. But presumably, if this mechanism was indeed the one that operated, we would expect to see the rate vary linearly with the concentration of methyl iodide. And if we wanted to, varying linearly would be enough to say that, okay, this molecule is involved in the rate determining step. But if we wanted to be even more precise, technically, if you vary methyl iodide, the slope should be rate constant times Cn minus. And so you could do multiple different concentrations of Cn minus, which we're keeping constant. and presumably the slope would vary with that too, and that would be another indicator. We can also keep Cn minus, methyl iodide constant and vary Cn minus, and again we would see a linear relationship. Okay, the other alternative, as we discussed, was this breaking the carbon iodide bond first. So leaving group leaves, and that's step 1, or A, whatever we're going to call it. And then in the second step, and only then in the second step, do we get Cn minus coming in to make the new carbon-carbon bond. Notice that the arrows are only happening, indicate that only one thing is happening at a time. In other words, I don't show an arrow from cyanide to this carbon because I need to communicate that iodide leaves first, you get a carbocationic intermediate, and then Cn minus attacks that. There would be 2 transition states, one reflecting the fact that I minus was leaving, that's transition state A, and another reflecting the fact that Cn minus was coming in and forming a new bond. Probably the transition state for A is higher in energy than the transition state for B, because in A we're breaking a bond, but in B we're starting to make a bond. Some of you have asked what would happen. It's easy to identify the rate determining step here. It's the one where the bond breaks, and that makes some intuitive sense. But some of you have asked, what if the first step isn't the highest energy step? What if there's a hill here, then we go over an even higher hill there? The answer is there is a way to deal with that. I don't know whether you did this in 105, 106. I'm thinking probably not. It's a set of assumptions that involves a rapid pre-equilibrium. If that doesn't even sound familiar, you can forget it because we're not going to really encounter having to write rate laws for situations like that. But we said that the only thing involved in the first step, the rate determining step, is the alkyl halide. And so that alone appears in the rate law, and therefore we call this reaction unimolecular. It's still a substitution, and it still involves the nucleophile, just not the nucleophile and the leaving group at the same time. And you could experimentally verify this by changing the concentration of methyl iodide whilst keeping Cn minus constant, and you would see a linear relationship. But if you held the methyl iodide concentration constant and then changed the Cn minus concentration, you should see nothing. Okay. People occasionally ask, how is that even possible? Because obviously if you don't have any Cn minus, you can't do the reaction. And the answer is that there's a more complicated rate law you can use that more accurately describes the situation, but at higher and reasonable concentrations of Cn minus, the Cn minus term drops out of the rate law, cancels itself out. Okay, so those are our 2 mechanisms. Any questions you want to ask overall about that? So probably the one thing is bothering you is, okay, great, I've got 2 options. Let's just make the world more complicated. How do I know which mechanism is operating? And so we're going to talk about that. Before we do that, I want to just talk about things that might influence the rate of the SN2 reaction versus the rate of the SN1 reaction. Okay, so I'm just going to copy this again because I don't want to, oops, thought I was going to copy it. I don't want to draw it again. At this point, I could have drawn it again already. Okay. So one interesting feature that I've shown you here is that the Cn minus attacks from exactly opposite the leaving group. All right? And you could presumably have proposed an alternative in which perhaps Cn minus came in from the same side as I minus was leaving. Maybe a transition state like this. And we can do an experiment to tell which of those options it is. And that experiment, of course, we can't actually do with methyl iodide because there's no difference in the products whether the Cn minus comes in from the same side as the iodide leaves or the opposite side. Do you see how those options are the same? Yeah. All right. So we could do an experiment, or rather, can you think of an experiment we could do that could tell the difference between these two potential pathways? Go ahead.
Just increase the reactants individually and compare the new reaction rates.
Okay, can you compare reaction rates? Yes, you could do that. Would that, if the product is the same, so presumably you're going to monitor appearance of product. So how would you be able to tell which one happened?
If you only increased one of the reactants and it didn't increase the rate of reaction, then the overall reaction would be first order.
Right. Oh, yes, that would absolutely tell you that it was this SN1 type mechanism where we break the bond first. I guess my question is about how you could tell whether the nucleophile came in from behind or came in from the front.
Okay.
Yeah. Other ideas? Go ahead.
Just make the leading group just like super, super big, and then it'll make the nucleophile less likely to approach if it's approaching on the same side.
Okay. Can you make the nucleophile, or sorry, the leaving group super, super big and
if it's approaching next to it, then it'll make it less likely.
and then you'd predict that would slow the reaction down if you approach from this side. That's interesting. I actually hadn't thought of that, and I think that could work. You'd have to have some way to modify the size of the leaving group without sort of changing its ability to leave. So I think that's a good idea. I need to think about it before I come up with a proposal on that. But that you're thinking along the right lines. Any other thoughts? Go ahead.
Are you able to measure the energy? Because I'm assuming it requires more energy to come at the same side than the opposite side.
Okay, can you measure the energy of the transition state? No, you can calculate it. Why do you suspect this transition state to be higher in energy than this one?
Well, because the Cn is trying to get in on the same side as iodine. Iodine is a huge molecule comparatively.
Okay.
So it basically has to kind of shoulder it out, while on the other side it just has to compete with proteins, well, protons.
Protons, yeah.
Protons
Okay.
are like super tiny and
Okay.
I assume relatively easy to push aside.
Okay. Yeah, so you're getting to the issue of sterics, and maybe it's easier to attack from the backside because of the size of the leaving group. And another way you could test that still would be to also increase the amount of substitution here on the protons to put other groups there. One reason you might, any other thoughts about why you might expect this to be higher in energy? Yeah.
Maybe just negative charge repulsion.
Yeah. You've got some, I don't know how to indicate this, the X of doom, I'm not sure, but you've got some electrostatic repulsion here, presumably, because those two partially negatively charged groups are nearer to each other versus here being farther apart. And yes, you can calculate transition state energies. I won't tell you what the answer is. Well, I guess you can figure out what the answer is because that's the one I drew first. But yeah, you could do the calculations and verify that this transition state is lower in energy than this alternative. Okay, any other thoughts about how to tell experimentally whether we get one versus the other? Yeah.
I don't know if you can do this easily, but if you swap negations with a hetero atom.
Okay.
The product, you can tell by the configuration.
Oh, stereochemistry, right? So what if let's see, let's instead of doing just methyl iodide, let's keep a hydrogen here. Let's maybe put a methyl group here. And just to keep things sane, let's put an ethyl group here. All right, so let's draw, let's see if, how are we going to do this? Put it here, and then we'll say if Cn minus came in from behind, mechanism would look like this. The transition state, remember the transition state for the concerted reaction has the nucleophile on this side, the iodide on the other side, and then notice that the geometry of the carbon in the middle is roughly trigonal planar. It was above, and presumably it's something similar to that down here. Okay, and then as the reaction proceeded and we start to make this bond, the carbon cyanide bond is going to be on the left side, and then the groups on carbon, while still having their same relationship relative to each other, are now angled towards the right instead of the left. So it's kind of like we've inverted an umbrella. I don't know if you've ever done that. Like, frankly, I don't ever let my children play with umbrellas anymore. Not because they might poke their eyes out. I'm not so concerned about that. Right, but because they'll break the darn thing, so we hide our umbrellas. Yeah.
Could you maybe put a sp hybridized carbon instead of a carbon triple bond, because that would be 180 degrees.
Oh, okay.
The iodine, so it prevents it completely from.
Okay. That's a good idea. So let's see. What if you did something like this? Would that be prone to substitution? No, not a good alkyl halide for SN2. Great. And there are actually some other examples too. It turns out that if you were to make an alkene like this, you also can't do it. And if you were to make an aromatic halide like this, you also can't do it. And in each of those cases, backside attack is sort of prevented by the geometry. Here, you'd have to be in the place of this carbon over there, so you simply can't do it. Here, you've got some steric problems because you have to approach close to this group, really close to the doubly bonded carbon, and here you have to actually get inside the benzene ring, and there's too much repulsion. You can't get in there. So yeah, that's in support of the fact that you have to have backside attack. Maybe we don't need to totally go through the other option, but let's maybe draw what we would expect front side attack to look like. What would the product of the front side attack be? Which direction are my methyl and ethyl groups going to point, and where would my cyanide be? Okay, still towards the left. And then Cn minus would be here. Do you see how that's sort of the natural consequence of that transition state? Cn just occupies the same spot that iodide used to. Okay? Now, use your newfound stereochemical knowledge to tell me what the difference between these two compounds is. Oh, they're enantiomers. If that's difficult to see, simply take this one, put it there. They're mirror images. Each of those carbons is attached to, the carbon in the middle in the center is attached to 4 different groups. I'm not sure why that hydrogen's hanging out to the side. That's irritating. Each of these carbons is a stereocenter. They are mirror images of each other, so you know that they're chiral and that they're enantiomers of each other. You could also redraw this molecule to look like this, and this one to look like this. And then we could redraw our starting material to look like this. So what we see if we have backside attack is that we get inversion of stereochemical configuration. Now that may or may not be the same as switching from R to S. It depends on the priority of the group that left versus the priority of the group that comes in. But the relative stereochemistry changes. I minus used to be coming out toward us when we drew the molecule this way. Cn minus is going back into the page away from us when we draw the molecule this way. Okay, so if the front side and the back side attack compounds would give enantiomers, now propose an experiment. Once the reaction's done, how do you tell which enantiomer formed?
You could do the experiment with a polarimeter.
Yeah.
And see if it's refracting light. If it's more than 0, the SPD refracts light once, then it's gonna.
Yeah. You can do optical rotation to see, the optical rotation experiment. Now, I suppose you'd have to know ahead of time what to expect, and then it would be very clear which enantiomer had formed. If not, you've got some more work to do, and one of the things you can do is X-ray crystallography. You can try to make a crystal of these compounds and then shoot X-rays through them and get a three-dimensional picture, and then you can tell. Okay, so the answer is when you do these experiments, and the mechanism is concerted, SN2, the evidence is, to summarize, that SN2 proceeds via backside attack of the nucleophile, opposite to where the leaving group is, and it proceeds with inversion of stereochemical configuration. And by that, I mean, maybe we need to put the term relative on there to qualify it because, but I don't know, maybe we just won't. I don't mean to suggest that it will always switch from R to S or S to R, because that's going to depend on the priority of the group that you come in as a nucleophile with versus the priority of the leaving group that left. But you will see inversion of configuration. If a group was up, coming out towards you, the nucleophile will replace it on the backside. All right, so that is the result. So we've described how and what, and you can memorize all those facts, but it's also helpful to know why, because if you know why, sometimes the how and the what just fall out as consequences of the why. The analogy, if you've taken physics as a high school student without calculus, you were memorizing Newtonian mechanics formulas. But if you took physics with calculus, all you had to know was the definition of velocity and acceleration, and you can completely derive the equations yourself. Fortunately, we don't do calculus in this class. We're not talking about deriving equations, but the why something happens can explain the how and the what. So the why behind the substitution reaction has to do with, of course, thermodynamics. We're forming more stable bonds than we break. But also it has to do with the HOMO of the nucleophile attacking the LUMO of the electrophile. So we need to know for any given set of starting materials, what's the nucleophile, what is the HOMO of the nucleophile, and what's the LUMO of the electrophile. In the case of Cn-, it's lone pair on the carbon, which you can draw in, you could draw it in an sp hybridized orbital, and that would be fine. I typically don't bother because as long as I've got the lone pair there, it's totally clear. What about our alkyl iodide? What is the LUMO of that molecule? Okay, the carbon iodide bonding or anti-bonding orbital? Anti-bonding orbital, that's the one that is empty. And if we were to draw that orbital, what that would look like, as we've done before for sigma star orbitals, is small lobes pointing towards the node, which is this dotted line. Recall that the node is a place where electron density goes to 0. And then large lobes pointing out away from the space between the two atoms, such that if you filled this orbital, electrons in it would tend to pull the atoms apart. That is an example of a sigma star. Notice that the sigma star is on iodide and carbon. You had an exam question on this on exam 1. Why should I attack the sigma star on carbon versus on iodide? So I minus is more stable than the other alternative. If you attacked at iodide, you'd have some kind of secondary carbanion as a leaving group. And you know from your pKa table that a carbanion conjugate acid is an alkane, pKa 50, is much, much, much less stable than I minus. Conjugate acid is HI, pKa minus 11. So much better to attack on carbon. Knowing that, then, where is the only place I can attack carbon? Can I attack the LUMO at carbon? The only place is from the backside. Okay, so if you understand the arguments, the Y was homo attacking LUMO. We also had some pKa arguments in there about what the most stable leaving group would be. But if you know what the LUMO is, then HOMO attacks LUMO. You attack an antibonding orbital. That reminds you that I minus has to leave. And the fact that you're attacking from the backside, because that's where the LUMO is, tells you that you're going to get inversion of stereochemical configuration. All right? And let's see. I guess we can go to the Spartan app. Sure. And I'm going to see if we can draw. Don't know that it'll have the iodide. It might have the chloride. Oh, good. The LUMO is the carbon chlorine sigma star. Up at the, I guess I need to get the laser pointer out. So these are the results of calculations. Here is the carbon-chlorine bond pointed downward. We can turn that off, right? You can see there's a carbon-hydrogen bond coming out at us. This is the sigma star. You see the changes in color representing changes in wave function sign. There's a node in between the two nuclei. Notice that there are also nodes at the nuclei, but those were present in the hybrid orbitals that were used to make the sigma bonding orbital and the anti-bonding orbital. And again, even though there's plenty of LUMO on the chlorine, we know we want to attack carbon because Cl minus is a better leaving group than a carbanion. Yeah.
Are there any cases where they do a front attack? I'm assuming you brought this up to show us that.
Yeah, are there examples of front side attack in a concerted reaction, substitution reaction? Yes. In fact, physical organic chemists have made it a quest in life to find all the exceptions to the rules. And you won't encounter any in this class, and I'm not actually familiar enough with them to even tell you when it happens. Yeah. Okay. Yeah.
So the optical inversion, that, I think you said this, but you may have not misheard it. That depends on the relationship or the comparison between leaving and joining groups.
Whether or not, well, what I was. Right, so the question is about stereochemical inversion because of backside attack. I guess let me just illustrate this. Oh, where did, Oh, there it is. Interesting, sorry. Put it away. We can assign R versus S at this carbon. Iodide is the priority group. This is the next one. This is third, and protons in the back away from us. So this stereocenter is R. And this stereocenter continues to, well, this stereocenter is S. That's because this carbon compared to the other carbons, this one's bonded to nitrogen, and so it's the high priority group. And again, we go clockwise, but protons coming out toward us, so that would be S. So yes, in this case, the nucleophile the leaving group that left was the highest priority group, and the nucleophile that came in was the highest priority group. And when that's the case, R will switch to S and vice versa. However, if you came in here with something that's lower priority than any of the other two groups, the configuration still switched, but you might not get a convenient R to S answer. Again, I don't think you're going to encounter that a lot, but the key thing you want to watch for is the place, does the nucleophile come in the opposite place of where the leaving group was? All right. Anything about that make you more uncomfortable than you usually are in this class? I was going to say make you uncomfortable, but yeah, go ahead.
Could you explain again the whole thing about carbon and the leaving group is more stable?
Oh.
Having the I lead is more stable than the carbon.
Sure. Okay, so where did we draw? There, sure. So if we do this and we attack at the carbon, we form a new CN bond, and I minus is the leaving group. If, in contrast, I'm not going to draw attack at iodide, I'm just going to write if we attacked at iodide. No, I guess I have to draw it now. Dang it. Whatever. CN minus. We would form a new bond between carbon and iodide, and the thing that would leave would be this negatively charged carbon, and then we would form this molecule. Now, you don't know this, but I happen to know that's an extremely reactive and electrophilic molecule. You can't buy it. You can buy the bromo version of that. But in any case, all you have to do, without even worrying about these compounds, you could look at the stability of the leaving group in either case. I minus is a good leaving group because it is the conjugate acid. It is the conjugate base of a strong acid. HI has a pKa of minus 11. In contrast, I minus is a terrible, horrible, no good. You guys maybe didn't read that book when you were little. Very bad leaving group. And it wants to move to Australia. And you can tell this because it is the conjugate base of a terrible, horrible, no good, very bad acid, which is butane. Nobody orders a balloon of butane to use as an acid. And the reason not is because its pKa is 50. So you've got 60 orders of magnitude favoring this situation versus that one. So yeah, that's why we don't attack at the iodide. Anything else about that picture that you're wondering about, or you wonder why it's that way? No? Okay, I'll bite then. The LUMO, I told you before, the LUMO is the carbon chlorine sigma star. What are you noticing about those hydrogens adjacent to the carbon chlorine bond? Go ahead.
The nodes are, I guess, shifting so that the electrons don't get in the way of the iodide, or I guess the loop on that.
Okay. What do you mean by that?
So normally we should have more of a dumbbell shape, I guess, interaction, even with hydrogen, spherical, but they're being pushed away from.
Okay. I mean, you are seeing nodes in between here, but my question is, why is any of the sigma star on those adjacent hydrogens anyway? It's supposed to be just the carbon chlorine sigma star, right? And the answer is, this is why we need to add hyperconjugation to our valence bond theory / MO theory model, because this is actually the result of a pure MO theory calculation. But you can see that this might have some significance, right? Because if some of the LUMO is on those adjacent hydrogens and you're the nucleophile,
You attack there.
could you not attack there? And would you have to choose between two options? And we'll see that actually that's a real thing. A nucleophile, depending on whether it prefers attacking carbon versus hydrogen, will have both of those options. And in a little bit, I'll show you what the result of attacking at hydrogen is. But in the meantime, I want to talk about why there's LUMO there in the first place. Okay. But do you all see how you've got some LUMO there on those adjacent hydrogens? Okay, a little bit of terminology that'll be helpful to us. We're going to call the carbon that's adjacent to the chlorine the alpha carbon. And then carbons that are adjacent to the alpha carbon we will call beta carbon. And here we notice that these two beta carbons are not identical, which is fine, and that'll have some implications later. But you can see that some of the LUMO is out on what we will call beta protons. That is, those protons that are attached to the beta carbon. Okay, so let me show you how we get that conclusion, or rather how we remind ourselves that this is occurring. So we'll redraw our molecule, and instead I'm going to try to do this in a way that illustrates the point rather than, I'm going to redraw the molecule. I'm hopefully not going to get the stereochemistry wrong. Maybe I will. I don't know. I'm getting kind of nervous. Would the methyl group be up? Okay. All right, so the view I'm taking of this molecule would be as though we were looking at the molecule from sort of this angle. So the carbon-chlorine bond or the carbon-iodide bond is in the plane of the page, and we're in a staggered conformation, and so you've got a proton here that's anti to the chlorine group. And we're looking at one of the protons that's on the beta carbon of the ethyl group. All right, so I'm going to draw the sigma star anti-bonding orbital. As we've said before, you have a lobe here, a lobe there, here, and then on the back side. Maybe we'll use the colors that Spartan uses. So sort of red here and here, and then blue here and here. And that's the empty sigma star. Okay, and what we're going to add now to our understanding of LUMO is that you have to also account for hyperconjugation. All right, so what does hyperconjugation tell you? It tells you that when a filled orbital can line up with an empty orbital on an adjacent atom, you get a favorable and stabilizing interaction. So this is the sigma star, and this is the carbon-hydrogen filled sigma bonding orbital. It's got electrons in it.
So
Okay.
that's not anti-orbital.
No, the one here is a bonding orbital. The one here is an empty antibonding orbital. Okay, so when a filled bonding orbital can overlap with an empty antibonding orbital, we get what's called molecular orbital mixing. In a sense, what we're going to do is take the sigma star bonding orbital, which is way high up here in energy, sigma star antibonding orbital, which is way high in energy, and then the sigma bonding orbital, which is really low in energy. The sigma star is empty, the sigma bonding orbital is full. They're going to mix together. We're going to do the plus combination, which is the in-phase combination. And the mixing is going to be not that stabilizing because, of course, the two orbitals are really far apart in energy. So the interaction is not strong. The resulting orbital that you would get from that plus mixing combination would be like this. We could draw it schematically like that, sorry. But if you were to actually sort of try to draw what the new molecular orbital would be that accounted for that filled carbon hydrogen bond interacting with the empty antibonding orbital, it would look something like this. You'd have the electron density in the carbon hydrogen bond would be spread out a little bit onto the neighboring, spread out a little bit onto the neighboring carbon, which would actually tell you that there's a little bit of maybe semi-pi bond character there. It's not a full-on pi bond, but it's like the electrons are leaning a little bit. They've spread out just a little bit. Yeah?
I know you probably answered this before, but how does that make it more stable whenever the electrons are going into an antibonding orbital? Wouldn't that cause it to break apart?
Well, so yeah, the question is it going to be, why is it that you're putting electrons in an antibonding orbital? Aren't we going to break that apart? That would be true if all we were doing was putting electrons into an antibonding orbital. But this is subtly different from that. We are mixing two orbitals together. And so what you're going to see is that mixing, we haven't dealt with the minus combination. So the antibonding orbital is still there. It's just higher in energy than it used to be. So what this does is it takes the electrons that were in the bonding orbital and spreads them out a little bit, allows them to move out a little bit lower in energy. By the way, if this conclusion is bothering you, that's okay. Don't worry about it. It's not that important. If you want to know more, I can tell you. What about the minus combination? What would that look like? So let's copy what we drew here. But let's draw the minus combination, and that would be where you add them together but out of phase. So we could put the H blue, and then maybe there'd be a little bit of red there. And that would be what the new sigma CH minus sigma star CI looks like. Maybe put it here so it's by, and it's empty, but now it's not only on the carbon and the iodide, it's also on the adjacent hydrogen. Notice, I mean, you can't see that, but notice what we did here for the minus combination agrees completely with what we get here in the phase relationships. I've always wondered actually why, if some of the LUMOs on the hydrogen, why it's still, why it's not, why it has an opposite phase. And the answer is because this comes from the minus combination wherein you add the adjacent CH with the sigma star antibonding orbital. All right. And the difference, of course, between what we've done here and what's shown in Spartan is Spartan shows this happening with the other beta hydrogen at the same time. And all you need to remember now, I mean, you don't actually have to go through this whole process anymore and consider the MO mixing. Really, that's probably non-essential background information. You just need to know that hyperconjugation, and in particular this one, this is sigma to sigma star hyperconjugation, allows the electrons in the sigma to spread out a little. A little is not one word, but I'm not going to correct that. And that's stabilizing for reasons we discussed at the beginning of the semester. And second, the LUMO spreads out onto the beta hydrogens. Okay, and if you can remember that, then you'll have this, the result of high-level quantum mechanical calculations in your mind without doing any math at all. So with the ideas we developed from the beginning with valence bond theory, and then the idea of antibonding orbitals, and now finally the idea of hyperconjugation, we're qualitatively coming to the conclusions that calculations give us. And this gives us a lot of predictive power. So yeah, the consequences are the molecule's a bit more stable, but the beta proton has some LUMO on it. All right? Okay, anything you want to ask there? Okay, notice that the beta proton that has LUMO on it in our drawing from Spartan, I'm going to turn off the orbital now. Notice that that proton is anti to the leaving group. Why isn't it on any of the other hydrogens very much? And the answer is because those hydrogens aren't lined up very well with the sigma star. Orbital mixing works best when orbitals are either end on end or side by side parallel. Go ahead.
Did you say this was the out of phase, and that's why it's different colors?
Yeah,
Okay.
that's right. This is the minus combination of the filled bonding orbital with the empty antibonding orbital.
And is it hyperconjugated with both?
Uh-huh. Yeah, both all of the any and all of the beta hydrogens that can align with the sigma star can hyperconjugate with it. Thankfully, we're not asking what to do when you add 3 orbitals together, because that would be kind of painful. So we're not going to do that. Okay. All right. So I think that's probably a good place to pause. I think your minds are sufficiently filled for this hour. So let's go ahead and pause, and we'll start up again at the top of the hour.